So now I've moved on to doing part 5.2, but I've also changed one more thing. So now I just ran a little jumper here. So I was previously using as +9, which was my substitute for +15. I'm just making that +5. So I have +5, +5. Here I have +5, +5, ground, and -5. So I'm using entirely the power provided by the analog discovery 2 board. So I don't need plus or minus 15. So here are my power supplies, and I have +5 and -5 going there. And then, so I've set up, so basically now we have a signal source going directly into one side, the source side of this analog switch. And then here's the drain side of this analog switch. And here's a 100 kilo ohm resistor to ground. And we're looking with the scope over here. I'm also looking with the scope at the signal we're sending in. And now if the switch is closed, then you should see the input signal here. If the switch is open, open means disconnect, close means connect for a switch. So if the switch is open, then we should see nothing here. Now the feature we're supposed to look for, the artifact we're supposed to look for, is that if the switch is open, so it's off, then there's actually a little bit of a capacitive coupling between the input and the output, between the source and the drain. So a little bit of the input signal, or maybe the derivative of the input signal, will bleed through from one side to the other just because there's a finite capacitance between this source and this drain. So we're going to look for that. First of all, and now this is pin 15. Pin 15 decides whether the switch is open or closed. So here is pin 15, and I have it now grounded, which means that the analog switch is open, so I see nothing at the output. The blue curve is the output, the yellow curve is the input. So in other words, the yellow curve is S1 and the blue curve is D1. Now if I move this to close the switch, I'll move this over to +5 to close the switch, then you see that the blue and yellow curves perfectly overlay one another. So it looks like it's behaving very well, very nicely as a closed switch. So D1 shows the same thing as S1, which is what you expect from a closed switch. Okay, now I'm going to go back and I'm going to open the switch. So when I open the switch, now, okay, you see nothing there. Fine. This is a 1 kilohertz sine wave. So Tom says, well, why don't you try like a 100 kilohertz sine wave? And then we'll look at the output. Now, of course, we have to change the time scale. So let's go to something like that. Okay, and now you see that there's a little bit of a copy of this sine wave appearing at the output, even though the switch is open. And it looks like it's probably phase shifted. Let's make this a little bigger so we can see if it's phase shifted. Yeah, you can see a phase shift there. So, well, it's not a huge phase shift, but you can see something of a phase shift there. Okay, now we'll go back to being on the same scale. And then let's try a kind of intermediate frequency, like, let's try like 10 kilohertz. Okay, then we look over here and you see a much smaller effect because capacitive coupling is biggest at high frequency. That's that impedance, like 1/j omega c, that omega downstairs. So capacitive coupling is a bigger effect at, whoops. Oh, you can still see something though, there's a little bit, okay. But it's much smaller because capacitive coupling is a bigger effect at high frequency, a smaller effect at low frequency because of that 1/j omega c, whoops. Let me zoom in just a little bit here. Well, here. This is probably the best view. Okay, now what I think is pretty interesting is if we switch this to a square wave. Now you know a square wave has lots of high frequency content. And then you see that, see the yellow signal is the input, it's on the S side, and the blue signal is the output, it's on the D side. And you can see the little spikes, so it's like the derivative of the input signal gets through. When you see the derivative showing up, two things they're not supposed to be talking to each other, and yet what you see on what you see on the victim in Tom's colorful electronics language is like the derivative of the perpetrator. So you see the bad guy here, and you see the derivative of the bad guy showing up. That tells you there's some kind of capacitive coupling between the good guy and the bad guy. And I can try that with the switch closed. I haven't tried this yet, but if I do it with the switch closed, of course you should just see that nice square wave. Yeah, you see the nice square wave just getting through fine. But you see when the switch is open, nothing is supposed to get through. And yet we see the derivative of the signal getting through, indicating that there's some kind of capacitive coupling. So that is the effect that Tom wanted us to see. There's some finite capacitive coupling between the input and the output. And again, this worked without any magical batteries. We just used the plus and minus 5 volts from the analog discovery board. So that's kind of neat to see that we can do that.